Hello engineering students, Mr. O again, and I'm going to go through an example and climb into the method of sections. Method of sections, we've gone through most of these and we've just finished method of joints, but now I'm going to move into method of sections. Method of sections operates probably a bit differently to what you would expect when it comes to method of joints. Now, what method of sections does is it goes by certain principles, which says if I have this is a little truss bridge here, it's a little Warren truss, which is really signified by its little triangles in this particular shape. And what this particular approach does to solving the force in members is that it says, number one, at any of the joints or at any point on a truss bridge, if the entire truss bridge is in equilibrium, or the truss is in equilibrium, then at any point there is equilibrium. And if that is the case, then instead of doing what we were doing in method of joints, where we then go and solve every single member's force and direction, compression or tension of that member by looking at each individual joint and finding each one, what it's saying is we can look at individual ones, because we can, instead of doing sine, cos and tan all the time for each individual joint, what we can do is we can solve using moments. Now it gets a little bit tricky, so I'm going to try and give you an idea of how that works. So here's my example, and if you get an example of this type of Warren truss bridge or any type of truss that looks like this, there's going to be support somewhere. Now, normally, in some cases, you might not get the support values, but in some cases, you might do. I don't know why that says P there. That should really say C. I have no idea why. Anyway, so let me go into the explanation. What method of section says is we're going to use moments. We're going to use moments to solve for the forces in each of the members, but we're not going to have to solve every single member's force. You will be asked in solve method of sections, solve for only that one, and that one. So in this example, you're being asked to solve for the forces in DE, BE, and BC. I don't know why it said P. BC. DE, BE, and BC. So what that's saying is, okay, the technique is what we do is we take like scissors and we cut through this truss. I'm going to take my little handy little post-it note, and we only work with the external forces on this particular truss that are on the left hand side, and we're only going to be working with D and whatever was E, a little what's left of it, B and what's been left of it, BE, and BC. Just be wary though, we might not be using any of the other trusses, other members in this place, in this section here, but what we will do, if we section that section off, but we might actually use some of the joints. So what I'm going to do is I'm going to redraw it. I'm going to first say, what am I looking for? I'll put them up there, and I'm going to redraw this. So I'm going to redraw this, but I'm going to do it as if I am now sectioned off the area. I've cut through with scissors the members that I'm going to be doing. We're going to be using. So, and that's effectively what we're going to be using. D, A, B, and I'm going to do a dotted line up to this joint here. So it's kind of not there anymore, but be warned, we might actually use it still. Okay, and we want to solve for DE, BE, and B. And again, I don't know what I'm doing, C. There we go. We've been told already what the forces are here. That's pretty awesome. So my force at A, we've been told what our supports are. So 8.75 kilonewtons. Normally we just do moments around that. We've got our force there, our external force there, and our external force there. So we'll be able to solve that. There's an external force of 10 kilonewtons. We know that there is or was one up there. And we also now know that there's a force there of 8.75. Distance-wise, he's also told us that there's a 5 meters from there to there. And because of that, they've also said 6 meters to there. So we know that this is, again, the particular type of triangle where those two are going to be the same distance. 6 meters to there and there. I feel like a bit of a fool that I've forgotten what that triangle's name is. There we go. So we have our triangle, and we want to solve for this one, this one, and this one. That's why we've cut through there, and we've discarded the rest of that. And how we do this now is, well, one thing I think that is missing here is we don't actually know what the angles are. Knowing that that angle is going to be equal to that angle, and that angle is going to be equal to that one, because of the type of triangles that we have there. If the bases are the same and the heights are the same, that angle is going to be the same. But let's work that out quickly. So very quickly, I'm going to find out what theta is. Oh, I drew a 6 theta. And so I'm going to write here, find theta, because we know that I have the opposite, I have the adjacent. Opposite of adjacent is tan theta, and I want to find what theta is, so it's going to be tan minus 1 opposite divided by adjacent. So what's my angle? There we go. 10 minus 1, 5 divided by 6. There's a nice round number for you. 39.8 degrees. You know what, I'm going to round this off to about 40 degrees. Okay, so my angle is going to be 40. 40. 40. So the technique works like this. The first thing you do is you find a point where you can do moments, but you use a point in the beginning. Your first step is to use a point where two of the unknown members connect or intersect. So I can use, so DE and BE connect at this joint, this little ghost joint called now E, and BE and BC join at B. I'm going to use one of those to start with, and I'm going to do moments about that joint. And let me show you how I'm going to do that. I'm going to start with E. So I'm going to call this step 1. And if I'm going to take moments about step and point E, by choosing E, let's look at the things I'm going to work with. I'm going to put DE, I got BE, and I got BC. When DE touch that joint, it is effectively cancelled out, and at BE, they are cancelled out because they are not going to be at 90 degrees of what I'm trying to solve here. But BC is not connected, it's not touching that joint at all. So what I do is I take that point and I draw the equivalent of like a beam. of my truss. And I look for, and I solve for moments about this point E of all the forces. I first look at the external forces, and then I look at the unknown force that I don't actually know of, okay? But at right angles to it. Let me explain this to you now. So everything that goes around, I create myself like a mini beam. And just like every so often when I solve for my forces, I put them in the equivalent there. Anything that's going to be going from my horizontal beam there, at that point, I do moments around that. And we know that, so I'm going to write here, sum of the moments E equals 0. I can also then have my little calculation, which says sum of the moments counterclockwise equals sum of my moments clockwise. Remember that moments is force times distance. So from E to my first external force, which is 10 kilonewtons down, what is the distance? Let's have a look. 6 meters. So from E to there, it's 6 meters. So I'm going to draw it here quickly. I'm going to go 10 is 6 meters to there, and 6 meters to there, so that's equivalent of 12. That's going to make, pivoting around my point E, my external force is going to cause that little beam that I've just, little mini beam that I've set up to rotate counterclockwise. So let's go counterclockwise. That's going to be 10 times 12 meters away. Okay, I'll put them on my counterclockwise side. What's my next external force? There's a force at that, this is the equivalent force there, even though my truss is really just that. At that beam, at that point there, if this entire beam is in equilibrium, if I apply a force there, it's equivalent as if it's perpendicularly at that distance away, causing my beam there to pivot in this direction. That is what? Clockwise. And how far away? So if E is there, 6, 6, 6, which is 6 plus 6 is 12 plus is 18. And that is, what is the force up? 8.75. 8.75 times 6 plus 6 plus 6 is 18. 18 meters away. 8.75. 12 plus another 6 gives us 18. Now this is where the trick comes in now. So I have both my external forces. This is an external force that's causing a rotation moment in my around point E over there, and then also and it's counterclockwise, and this is causing a clockwise motion, pushing it like that, wanting it to spin in this direction. But I'm not looking at DE because it's touching that point. I'm not looking at that, it's touching that point, but I still have BC that needs to be solved. And what I do is I look to see at that particular point, I don't know, at this particular joint there where it's connected, where B is connected, I don't know in which direction it is going. I don't know what its internal force is, the compression or tension, so I assume it's positive, I assume it's in tension, and therefore the arrow is going away from the joint at B. But it is perpendicularly that far away, pushing like that, 5 meters, and pushing in that direction. This is when you're going to have a bit more lateral thinking, and it's going to make it go counterclockwise. So that is force in BC times how far? 5. My counterclockwise moments is going to cause my beam to want to pivot in this direction. It's internal force. So I have an external force, and an internal force, causing a moment force in points E. And there's my formula. So 10 times 12 is 120 plus 5 FBC equals, and I don't know how to work that out, 8.75 times 18, 157.5. So I'll bring that over to this side and then divide by 5. Minus 120 divided by 5, 7.5. So it is positive, therefore it is in tension. So the force in BC is 7.5, and it is in tension, therefore the force is going that way. And that's it. I'll just solve the force in. I chose this point because these two touch that point. I don't use them. I use what's not used at 90 degrees to it. I'm now going to do the same with step 2. Again, I'm going to now choose point B. I've got DE, I've got BE, and I've got BC. Point B connects with BE, so that cancels out. It connects with BC, which leaves me finding DE, which is up there. Same process. What I do now is I draw my spot, which is B, and I draw a beam out this way. Straight away I can see that I have a 8.75 force, which is 6 and 6, 12 away from B, and that is going to be clockwise. So let me do that again. I got my I'm going to take, and I just stated, take moments around B, there at E, and my counterclockwise equals my sum of my counterclockwise moments is equal to the sum of my clockwise moments. So around B, going in clockwise motion will be 8.75, my external force at A, times it is 12 away. It is 6 and 6 away. So I'm at B, there's my force A, it is 6 plus 6, force times distance, 8.75 times 6 plus 6 is 12. 8.75 times 12. There we go, that's my clockwise. What about my other force? My other force is sitting up there. It is just to the left of B, actually right down in the middle. It is 10 kilonewtons, but it is only 6 away. But it is going to cause it to go counterclockwise. So that would be 10 times 6. And the other force that I now, which is DE, I don't look at that, it's touching B, and I don't look at that member, it's touching B. I look at that member there. I don't know which way it's going, so I'm going to assume it's positive, I'm going to assume it's in tension, and the force, internal force, is pushing away from the joint. And again, if I draw my moment like that, here's D, going away from the joint, being 5 meters away from that. My internal force, so this is my external, this is my external, counterclockwise, it is going to be pushing away from the joint. It's going to push my beam in this direction. So it's going to be clockwise. And the clockwise would be the unknown force 5, which is my distance, times force dE. And there we go. That's also clockwise. And that's a formula. So that would be 60 equals 8.75 times 12 plus, yeah, do it again. 105 plus 5 FTE. So that will be 60 minus 105 divided by 5, negative 9. I've solved the letter B. It is negative, therefore it is in compression. So I'm going to go back up here and I'm going to go FBC is 7.5 and it's in tension, and I know it's kilonewtons. FDE is 9 kilonewtons in compression. It's in compression, so the force is now, instead of being away from, it is going into the joint. And my last one is I'm going to probably go down to the likes of A. The reason why I need to go to A and not, let's say, to D or anywhere else is because all of my forces have been, at the point I've been working with, have effectively been at 90 degrees to a beam that I can place there and there as well. This particular force, this particular member is actually axial, at an angle. And I want to pass a beam through that point where it connects so that I can work out either it's vertical or it's horizontal in order to make a beam. Because when we do beams, in all the beam calculations that we do, we always resolve angled forces to be the equivalent vertical or horizontal. We never ever leave them at that angle. So what I'm going to do now is I'm going to take moments, it's my step 3, I'm going to take moments around A, and when I do that, I actually run my beam through B. This is what I'm trying to solve, and just like I do in my method of joints work, what I do is I find the equivalent of its horizontal, and in turn, because of that, this is the hypotenuse, and I find its value. And I know that it's going to be that value sine 40 degrees. So straight away, I'm sitting at A. I really can't use this external force because it is right at that joint. For some distance, its distance is 0, therefore I don't have a turning moment at that point A for that external force. And so using step 3, I'm going to try and solve for BE. It's only I actually want to solve left. What do I have? I have 10 kilonewtons down, 6 away, and that is going to be going in clockwise. So let me just do this. Sum of the moments around A. And I'm going to write this out here. I'm going to say sum of the moments counterclockwise. I don't normally redo it. Sum of the moments clockwise. This is going to cause it to go clockwise, so I'm going to say 10 times 6. That's that first external force. I can't use my other external force, but I must not forget that I now also have, up here at point D, I actually have an internal force that I've worked out, which is DE. So here's my one external, but it is going to cause a moment of A pushing in the counterclockwise moment or direction. So I've actually got, and how far away is it? It is over there. Five away. So I have force of dE equivalent of 5 away, causing a counterclockwise moment. So I'm going to put that there, which is, what is force dE? It is 9. I remove the positive and negative because I'm assigning a direction already with my formulas here. 9 times how far away? It is 5. So I have that force there. And what else do I have? I've done that one. I have done that one. But I now have an unknown, which is there. So what I'm going to do is, I don't know which direction the vertical component of that is going to be. 6 and 6 and 12 away. I assume it's going in that direction, which is, again, also counterclockwise. But it's now going to be force BE, which I'm trying to solve, sine 40. And that's it. I've got no other forces. And it is going to be, I must not forget. See, I almost made a mistake there. I'm going to rewrite this here so it makes a bit more sense. 9 times 5 plus FBE sine 40. That's just my force. I forgot the distance. It is, at that point there, it is 6 and 6 is 12. And my other force here, my other external. So this is my external force. And instead of having another external force, it was cancelled out by it being the moment around A. I actually got another internal force that I've solved. Okay. I can't use the force running in parallel to that beam. The horizontal, I'm already working all the vertical forces out. Okay, that causes moments. It's not causing a moment at all because it's traveling along with the beam itself. And this is my internal now that I'm trying to solve. So let's work that out. 9 times 5 is 45. Plus 12 FBE sine 40 equals 60. Hope you guys can still see this. So what that means is, I'm going to move over to this side. FBE equals 60 minus 45, because my 45 goes to the other side of the equal sign, and I divided by 12 sine 40. So 60 minus 45 will give me 15, divided by 12 sine 40. And that means it is plus 1.94 kilonewtons. It's positive, therefore it's in tension. And there we go. That's the answer. And I've actually got verification on my truss simulators to prove that this guy is actually in tension as well, and he is got a force moving away from that joint at B. So there's my method of sections. Literally in 3 little steps, instead of having to solve every single force in every single member, I've just solved those, but instead of using sine, cos, and tan And on my vertical and horizontal approach, I've just done it with moments, focusing on an area. So be cognizant of the fact that the process you follow, the last part is important, where if you're left with a diagonal, the first part, choose one where the two touch and you cancel them out and you find the other one. The same as when it comes to solving for B. I chose E to start with. Those two were touching. I can't work them out. I only find out what BE is, or BC. The same when it came to B. When I worked on B, those two were touching, those two members. Therefore, I solved for DE. In the last step, because I'm at an axial load, I have to choose a member. I have to choose a point that I have my moments calculation, my pivot point, with a beam that runs through the joint that it is coming out of in order to find its perpendicular. And so you work out the distance there. And of course, don't forget to use the other side, like I've done there. Hope that makes sense to you. There you have method of sections, looking at only the areas that you need, not all the others.